Okay, this is part 2 of our lesson on inflection points and concavity, and we're going to work through some examples. And this one says find the points of inflection and the intervals of concavity. To find points of inflection, remember that points of inflection are points where the second derivative equals 0 or does not exist. Well, I should back up and say potential points of inflection are points where the second derivative equals 0 or does not exist. We'll find out if they're truly points of inflection when we check the concavity. So let's look for potential points of inflection, potential inflection points, which I call pips. Let's look at those by setting the second derivative equal to 0 or seeing where the second derivative does not exist. So let's find the first derivative, and that would be 15x to the fourth minus 20x cubed. Let's find the second derivative, and that would be 60x cubed minus 60x squared. Now there's no place where that does not exist, so we just need to figure out where this is equal to 0. So set the second derivative equal to 0. Let's factor 60x squared out of both terms, and that would leave us with x minus 1 for the other term. You can divide both sides by 60, and then set each factor equal to 0, and you have x squared equals 0, or x minus 1 equals 0. So we get x equals 0 or x equals 1. Those are what I'm calling potential inflection points, pips. We don't know yet if they are inflection points. So here's what we do. We divide the number line into intervals, and we divide the number line at those points. So we have negative infinity to 0, 0 to 1, and 1 to infinity. This should remind you of the first derivative test, where we took the zeros from the first derivative, made intervals, and looked at increasing and decreasing behavior. It's very, very similar. We're taking these points, making intervals, and we're looking at concave up and concave down behavior. So now that we have intervals, we want to take a point in each interval and plug it into the second derivative. So let's see here. Let me move that a little bit. We want a test point. Let's choose x equals negative 1. Let's choose x equals 1/2. And let's choose x equals 2. We have to test it into the second derivative. So here's the second derivative in its factored form. That would be a great place to test. Okay, so let's take negative 1. 60 times negative 1 squared. So negative 1 squared is positive, times 60 is positive, times negative 1 minus 1. Negative 1 minus 1 would be negative. Positive times negative is negative. Second derivative is negative on that interval. Now let's take 1/2. 1/2 squared is positive, times 60 is positive. 1/2 minus 1 is negative. Positive times negative is negative. Now let's take 2. 2 squared is positive, times 60 is positive. 2 minus 1 is positive. Positive times positive is positive. Okay, so what does this tell us? This tells us that f of x is concave down because of the negative second derivative, then concave down again because of the negative second derivative, then concave up because of the positive second derivative. So we're looking for inflection points. An inflection point is a point where the concavity changes. So you have an inflection point at x equals 1. That's where the concavity changed from down to up. If you want that point as an ordered pair, because sometimes you might need the y coordinate as well, you would plug 1 into the original function and get its y coordinate. So 3 times 1 minus 5 times 1 plus 1. That looks like it would be negative 1, if I did that right. Okay, so find the points of inflection. We've got that. Find the intervals of concavity. Well, we have that in this little chart thing that we did, but we could just make it a little bit more explicit and say that f of x is concave down on the interval from negative infinity to 0, union the interval from 0 to 1, and we could say f of x is concave up on the interval from 1 to infinity. Okay, let's take a look at number 2. Again, find the points of inflection and intervals of continuity, intervals of concavity for f of x equals cosine of 2x. And we have a little graph to remind us what cosine of 2x looks like. It looks like the cosine graph, but it's 2 times the fun, so that means it was shrunk horizontally. So we have twice as many curves in the same amount of space. Okay, now if you look at the graph first, you can tell what the concavity is doing. You can see that it's concave down, and then it's concave up, and then it's concave down, and then it's concave up, and then it's, oops, I did that in the wrong color. Oh no, better go back. Can't have that. Concave up, and then concave down. Okay, we can tell, and so we can see that the concavity is changing at this point, and this point, and this point, and this point. So whatever those points are, we should expect those to be our inflection points. So it's kind of nice when we know what to expect before we even do the algebra. Now let's go through the process. So we need the second derivative, so let's find the first derivative. The derivative of cosine of 2x, we need to use the chain rule. So the derivative of cosine is negative sine, oops, almost forgot my negative, so negative sine of 2x times the derivative of 2x, which would be 2. So let's write this as negative 2 sine of 2x. Now we need the derivative of that to be our second derivative. Leave the constant negative 2. Use the chain rule. The derivative of sine is cosine, so we have cosine of 2x. And the derivative of the inside would be 2. Derivative of 2x is 2. Let's write that as negative 4 cosine of 2x. For the potential inflection points, we need to know where that equals 0 or does not exist. And there's nowhere where it does not exist, so let's just set it equal to 0. Let's divide both sides by negative 4. Now, we have to think about our trig here. For what values of 2x would the cosine be 0? I'm going to draw my unit circle. At 0 radians, we have the point 10. At pi over 2 radians, we have the point 0.1. At pi radians, we have the point -10, and at 3 pi over 2 radians, we have the point 0, -1. So where is cosine 0? Cosine is 0 wherever the x coordinate is 0. So that would be 2x would be pi over 2 and 3 pi over 2. Now, I don't know if you remember this from way back last year in pre-calc, but because we're about to divide these answers by 2 to get x by itself, we go around the circle a second time. We need our additional answers. So going around the circle another time would take us, let's see, if we're at pi over 2, we add a 2 pi to it, and that would take us to 5 pi over 2. And if we were at 3 pi over 2, we add another 2 pi to it, and that would take us to 7 pi over 2. Now we divide all those answers by 2, and we have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Those are the potential inflection points. Look at the graph. Pi over 4, 5 pi over 4, 3 pi over 4, 7 pi over 4, and, let me start that over. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. That makes sense for the graph. So now that we have those, we divide our number line into intervals, and we don't have to go back to 0 or back to infinity and negative infinity for this number line because we have the closed interval from 0 to 2 pi. So we go from 0 to pi over 4, from pi over 4 to 3 pi over 4, from 3 pi over 4 to 5 pi over 4, and from 5 pi over 4 to 7 pi over 4, and from 7 pi over 4 to 2 pi. What you want to do now is you want to take a number from each interval and you want to plug it in and see what happens to the second derivative. So here's our second derivative back here. Don't forget about the negative sign on it. Use the full second derivative. Don't use the one that we divided by -4. So you're going to take numbers, test them into the second derivative, and you're going to see whether you get positives or negatives. Okay, now here's a tip for what I might do to not get too bogged down in the numbers for this problem. I would probably type the function y equals -4 cosine of 2x into my calculator. That's the second derivative. And I would set my calculator to radians. And then I would find approximate numbers for each interval. For example, pi divided by 4 is approximately 0.78. So maybe I would use approximately, like 0.5 as my test number. And then for the next one, 3 pi over 4 is approximately 2.3. So maybe I would just use 1, and so on, etc., etc. Just use decimals, it's fine. And then you can use the table feature of your calculator to figure out whether you get positives or negatives for each of these. So what you'll notice is that the first interval for the so the first interval, you're looking to see what's happening to the second derivative. And you're going to get a negative, and you're going to get a positive in the next one, and a negative, and a positive, and a negative. So, do you have any inflection points? Yes, there was a concavity change at each place along the way. So we could say that f of x is concave down, then concave up, then concave down, then concave up, then concave down. So, what are the inflection points? They are occurring at x equals each of the pips. Pi over 4, 5 pi over 4, oops, I missed one, 3 pi over 4, and 7 pi over 4. And if you have to give the y coordinates, then you're going to go back and put each of those x coordinates into the original function. And then the intervals of concavity, you have concave up for pi over 4 to 3 pi over 4, union 5 pi over 4 to 7 pi over 4, and you have concave down for 0 to pi over 4, union 3 pi over 4 to 5 pi over 4, union 7 pi over 4 to 2 pi. Okay, I have a couple more examples. Let's look at number 3. This one is a rational function, f of x equals 1 over x, and here's a reminder of what the graph would look like. So if we look at the graph, we notice that there is a change in concavity. It looks like it's going to be concave down on the left side and concave up on the right side. And it looks like that change of concavity happens at x equals 0. So let's go through the algebra of it. So first we find the first derivative. Now let's go ahead and write the function as x to the negative first power. So the first derivative would be -1 times x to the negative second power. And the second derivative would be, bring down the -2, so positive 2 x to the negative third power. And we could write that as 2 over x cubed. So now we want to know where that equals 0 or does not exist. And we know when we have a fraction, you set the numerator equal to 0 to find out where the fraction is 0. You set the denominator equal to 0 to find out where the fraction does not exist. Well, 2 is not going to equal 0, so there's no number that makes this derivative equal 0, but there is a number that makes the derivative not exist, and that would be if you take the denominator, set it equal to 0, and solve, you get x equals 0, and so that is a potential inflection point. Now let's check the intervals of concavity. So we're going to go from -infinity to 0, and from 0 to infinity. Let's find a test point. Suppose we test x equals negative 1, and we test x equals 1. Let's find the sign of the second derivative. If I plug negative 1 into the second derivative, I get a negative. If I plug positive 1 into the second derivative, I get a positive. So there is a change in concavity, and we can say that f of x is concave down from negative infinity to 0 and concave up from 0 to infinity. Here's the thing about the point of inflection, though. If the point of inflection is not actually a point of your function, then you don't call it a point of inflection. So we would be tempted to say that we have an inflection point at x equals 0. However, we can't say that because 0 is not in the domain of f of x. It has to be a point in the domain to be considered an inflection point. Now, it's still, there's still a change in concavity, but we just don't officially have an inflection point. Number 4, f of x equals e to the x. We could visualize this one too. We don't even need the calculator for that. That looks like this. So, what do you think the concavity is? Tell me out loud. You're right, it's concave up. And where do you think the points of inflection are? I didn't hear that. Say that again. Oh yes, you're right. There are no points of inflection. That's what we're expecting to find out when we do it algebraically as well. So let's go ahead and find the first derivative. That would be e to the x. And find the second derivative. That would be e to the x. Now where does that equal 0? It does not. Okay, so that's why there are no inflection points. So our interval is just the entire number line, negative infinity to infinity. We can test whatever number we want. Let's test x equals 0. And we can plug that into the second derivative. And e to the 0 is positive. And so f of x is concave up the whole time. Ta-da! All right. I would like you to try these problems, and I will post pictures of the book in case you don't have the book, and I will post the worked out solutions and hopefully also make a video of me working out the solutions. Hopefully that will be helpful for you. Thanks everybody. Bye.